audio, of the volume of the camera.
Okay.
You can do this.
Just make it high. Just make it maximum.
No, the thing is that here's already clapping. So I will put it this way where you can monitorize with your cell phone. You can try to hear how it is.
But I need to have a earphone with me.
Okay, yeah.
Or
You don't have it?
I don't have a earphone.
Okay. Let's put it here. But I'm sure this is more than enough.
Okay, then it's fine. That's fine.
And what else? And that's pretty much it. That's it. And we can go here and say that's it.
Okay. Okay. Sounds good.
And what else?
I'll keep that with me, right?
Oh, let me show you this. So this, if you see, it has 99% of battery, but it's only 1 hour life of battery. So you have to connect it all the time because classes usually.
Yeah. So where is the plug?
Here.
We're close? So yeah, I just really follow some actually. Okay. Just a couple of
Yeah. You can use and here is the iPad charger. The iPad's charger.
Okay. So then I connect it to which point?
Then back here.
Let's go.
Yeah. This is what is going on YouTube. Thanks.
Okay. You ready? All right. Hi, everybody. How's it going? Welcome to Deep Learning. My name is Burton Earnshaw, and I'll be the instructor for this class. I am not a full-time member of the faculty. I'm an adjunct professor in the math department of all things, and I get to teach this class. So that's really fun for me. I did it last year in the fall. A couple of our TMs in the class, and I don't remember your name, but I know you're in the class. We're sitting in on the class anyway, so a couple of familiar faces. But this was really fun for me to do last year, and I'm looking forward to doing it again. We have 3 sections in this class. There's a math section, and there's 2 CS sections, 6,000 level, 5,000 level. So we've got all kinds of, well, not all kinds, we've got a few different backgrounds here, and worked out great last time, so whatever section you're in, it should be just fine. Why am I teaching this class? This is the question I don't really know how to answer for you. You have lots of competent CS faculty who could definitely do this, but they have let me do this. I think because I do deep learning for a living, and they don't. So I don't know. There maybe is some advantage to that, but you'll get to decide if that's the case or not. I was a student here at the University of Utah many years ago. I got my PhD in math here, math biology, and done a number of things since then, but I currently work for a local startup called Recursion Pharmaceuticals downtown in the Gateway Mall. And we generate tons of image data of cells, and we use that data to try to discover new treatments for diseases of all kinds. And I may have some opportunity to talk a little bit about that throughout the semester, but yeah, I'm not trained in CS, machine learning, AI. Don't have a degree in that. There weren't degrees in that in the Stone Ages when I got my degree, and so this is all just kind of like learning, as you go. So hopefully that doesn't disappoint anybody. Also, as an adjunct professor, and this is like fun for me. Like, I'm not here because this is my job. I'm here because it's fun. So I think that makes it good, but also this I don't have an office here. I don't hold office hours. We have 3 TMs in this class who have all either been a TM in this class, or they were in the class last time around. they'll definitely be able to help you. But it's going to be different for that reason. So if for some reason that doesn't feel good to you, just know that that's going to be the case. And it's not going to change if you complain. What else? Who here is doing machine learning already like in a job? Yeah? How many? Raise your hand high so we can see how many there are. Really? For those of you doing it, how many of you are actually doing like deep learning or doing like neural network training? 1, 2, 3. Cool. So maybe I'll teach a lecture sometime along the way here. There's all, these, a few years ago, no one was doing neural networks because it was like embarrassing to do neural networks, and all of a sudden, like, it's like the cool thing to do. Everybody wants to do it, and finding applications for neural networks in all kinds of things, which is really fun and exciting. And if you follow the literature, you follow kind of publications, and read about it, like you'll see new applications all the time. So yeah, it's a moving field. This class, we're gonna spend a lot of time at the beginning, kind of going through like very basic stuff around like how to train neural networks as well, like how it works, the mechanics of it. So like the optimization involved, how gradient descent and how that's done in backpropagation works. We're going to talk about convolutional networks a lot and how those work, and kind of get into some of the practical things around the tools for the software that exists for doing this, and then talk about like how to understand them. Then we'll do some generative models. We'll do some recurrent neural networks. We'll do a little bit of reinforcement learning. That would be the end of it. So, anyways, hopefully for those of you who are already doing this work, like that isn't too disappointing. That it's just going to be like it's in some sense introductory. Although hopefully you'll learn some things along the way. Okay, so what are we doing here? So, this is me. I'm bald, kind of getting old, and this is something you can do with neural networks. You can turn your face into like an animal dog-like thing, and we'll do some of this at some point in this semester. This is actually, some of you probably already seen this or read about this. This is like a way of sort of getting at, like, it's kind of a goofy way to do it, but kind of getting at like what a neural network is actually like tuned to recognize in an image. You can sort of like turn it around and make it produce the things it's wanting to or like it knows how to recognize. So there's actually a lot of animals in here. It's hard to see at the resolution. Recognize anybody in this picture? No, you don't recognize anybody? These all look like famous people to me. I'm like old and not cool, so I shouldn't know any of these people. You should know all these people. So none of these people actually exist. These are all images that were generated by a network that learns basically to sample from the distribution of celebrity faces. So, like, I think I recognize some of these people, and I realize that that's not quite that person. But there's something interesting here, right? This thing learns this was trained on data that was just faces of celebrities. And if I were to like look at this and step back, I'd say, you know what? These all kind of look like famous people, like celebrities, right? Like nobody here looks like they're down on their luck, Somehow, people got this neural network to learn what it means to like look like a celebrity, kind of like a general thinking. What does celebrity look like? Strictly from data of celebrity faces. Not only that, these are like really awesome images. Like they're really high resolution, and except for like a couple of kind of goofy artifacts, like this dude's hair is a little bit. If you just look at it a little while, like you just realize that doesn't look right. It might be right. It's kind of got like a Trump kind of like when it falls back maybe, but it's a little bit messy there. But these are really high resolution images. This was done by NVIDIA like a year and a half ago, and they followed up recently with this, which is kind of like it's the same kind of style of network, but it's like ultra high resolution images. So like these look like photographs. Like look at the hair, the stubble on this guy's face, the wrinkles. These are totally generated, and they're generated solely from having like been trained on. This is a Flickr faces data set. So scrape Flickr, just get faces, and then it was trained to generate these really high resolution images. Now it might not seem like really like revolutionary to like generate like a high resolution face until you like realize that all this is like a neural network that's just kind of learned from data. And then all of a sudden it's like extremely revolutionary because these people don't exist at all. And what's cool about these techniques is that you can like, the paper that I pulled this from doesn't have this, but there's like some sort of latent space that sort of encodes the features that are generating this face, and you can start to move around in this space, in this latent space, and then you get kind of like, you could like move yourself between this face and that face and see like all the interpolations along the way, but it's on high resolution like all the way. It's really, really, really amazing stuff, and also kind of scary. And we'll have some examples that are like scarier. That you can do such realistic things. Now, fortunately, this is just photographs. We're not producing like realistic 3D people yet, but I'm sure somebody's thinking about that. What's interesting about that image is that it basically, so like the first set of images of celebrities, the model there is called a generative adversarial network. What they did in that second set, which was even more high resolution, was to combine that with an idea that's been around for a little while, which is called style transfer in neural networks. Again, these are using some. These are trained in different ways, and we're actually going to do some of this in this class. But people have kind of figured out how to separate the content of an image from like its style, and be able to use neural networks to sort of take the content from one image, the style from the other, and combine them. Right? So we have these famous paintings, and now we have Darth Vader in the style of these famous paintings. Like what's going on here? What are these networks learning to do? And this is like the thing that we're going to be hopefully kind of building up intuition around. Like, what are these networks learning to do here? Like, how is it separating content from style? Like, what is it? How is that done? And we're gonna hopefully get at some of those things throughout this class. This is a little bit old now, but like this is to me really, really, really cool. So these are networks that have learned to take images and then automatically write captions for like what's going on in the image. So it's like it's learning something about like the statistics of the image, like what's in the image, and then how to associate that with the statistics of like natural language. And these are cherry-picked examples. They're all pretty good, right? Man in black shirt is playing guitar. I mean, that's how I would describe that photo. Construction worker in orange safety vest is working on the road. Yeah, I guess so. It's a Lego toy. Like it knew it was a Lego toy. I mean, like this is really cool, right? Like these things have learned just from data how to do these things. How is this happening? How do we have such powerful techniques now that can take a pile of data and learn to do these kinds of things and do it fairly accurately? Unless you think it's perfect, here's some examples of where it failed. This is not so bad. It's definitely a young boy. It's actually infant, but it's not holding a baseball bat. It looks like a toothbrush to me, but not so far off. The statistics, baseball bat and toothbrush, at least like as large as it looks compared to the baby's face, is maybe suggests it's a baseball bat to the network.
Where's the forest?
Yeah, I love I love it. So you don't see the horse? The horse is obviously right here, right? No, but think about it. This actually looks like a horse, right? There's this like, it's this, what would you call that? It's just something that's protecting the fire hydrant that's in there. It's like some sort of railing around it. But look at it. It's got 4 legs and this kind of like body here. And then there's this goofy bush right here that kind of it's giving it that corset, right? So it's not a horse. You and I know that right away. But just think about this network. This network hasn't grown up with horses and fire hydrants and yucca plants and things like that, around. It just has seen a pile of data, and to the best of its knowledge, that looks like a horse to it. And it's not that far off. And this kind of gives insight into what these networks are doing. These networks are learning something about the statistics of pixels and language and associating them together. I think this kind of stuff is fascinating and amazing that this is actually even happening. And you and I have access to these data sets and maybe to enough computation to actually learn to do these things. At any time you can stop me and ask questions, I'd be happy to answer. I love this one. There are networks that learn basically like the statistics of whatever kind of text you want to give it, and then learn to generate that text. So here's something that was trained on Harry Potter text, and it produced a whole book, an entire book of Harry Potter. Actually, it wasn't the whole book. It's actually just one chapter. Now that I think about it, but anyways, a whole chapter. So and it also came up with a title. And the title it came up with is Harry Potter and the Portrait of What Looked Like a Large Pile of Ash. That's kind of goofy, right? We know, I love this about studying this area, because we know immediately that's goofy, and yet that title is somehow following the statistics, the patterns of Harry Potter language. There are piles of ash. I don't know. There's portraits. There's definitely lots of portraits in Harry Potter. I'm a Harry Potter fan, so I'll just go ahead and admit that right away. So I know there's a lot of portraits in the books. I don't know. There's piles of stuff. There's definitely ash. Death Eaters and ash. I don't know. But if you start reading this text, it's really funny. And again, statistically, it's right. It is totally Harry Potter. But somehow, what it hasn't learned is this thing that you and I grasp right away, which is this is not semantically right somehow. The castle grounds snarled with the wave of magically magnified wind. That's almost right, except that it's not. You know it's not right away. These networks don't know that. What's the difference? We're not going to study that, but I love that question. You should go take a philosophy class next and think about that. But the sky outside was a great black ceiling, which was full of blood. I mean, not right, but there's lots of ceilings and blood and things like that here. If you just take a look at it, I just love this. So this was at the end of this chapter. So Harry could tell that Voldemort was standing right behind him. He felt a great overreaction. Harry tore his eyes from his head and threw them into the forest. Voldemort raised his eyebrows at Harry, who could not see anything at the moment. Now, that's really amazing right there. Those two sentences relate to each other. There's some semantic meaning, understanding there of if you have no eyes in your head, you can't see. That's pretty cool. Voldemort, you're a very bad and mean wizard, Harry savagely said. Hermione nodded encouragingly. The tall Death Eater was wearing a shirt that said Hermione has forgotten how to dance. So Hermione dipped his face in mud. Ron threw a wand at Voldemort. Everyone applauded. Ron smiled. Ron reached for his wand slowly. It's interesting. Ron always needs recognition in these books, right? This is sort of grasped, and I'm sort of stretching here a little bit, but when I read that, it's sort of grasped that Ron needs recognition. That's a kind of a statistical property it's learned to produce in the language. Ron's the handsome one, muttered Harry as he reluctantly reached for his. They cast a spell or two, and jets of green light shot out of the Death Eaters' heads. Ron flinched. Not so handsome now, thought Harry, as he dipped Hermione in hot sauce. I'm not sure why everybody gets dipped. The Death Eaters were dead now, and Harry was hungrier than he'd ever been. I would be hungry after a battle like that too. Yeah. Anyways, there's tons of stuff like this online now. There's so much of it.
Have you seen the New Age bullshit generator?
No, I have not seen that.
That one's good because it kind of like, it doesn't need that like narrative structure. It's like, oh yeah, I can see this in that.
Yeah.
I can see this.
Much like if it's just like kind of short, like New Age statements, way easier to do.
Right.
Way easier because you don't need to connect all the elements across vast, like textual space, right?
Right.
This is way harder to do, and done with much more sophisticated network. Probably, I don't know exactly what's going on.
Right.
That's the first question. So the input is just the book title, like Harry Potter, and then the output is the whole.
Well,
text, or-
yeah. So like you might be so there's a difference between the input and the seed. So when I say the input, I might think about all the training data that was used to train this, and that was like all the all 7 volumes of Harry Potter, probably plus whatever else I could find. Beetle the Bard or whatever was available at the time. That was like what was trained, but I don't know how it was seeded, but it was probably seeded with just a few statements like Harry Potter and then it starts to generate the text after that. And we're gonna do some of these things as well in this class, which is we won't do this, but we'll do something like it, and you'll get a feel for how this works. These are generally what are called recurrent neural networks that whose job is to learn like the temporal statistics of like sequential statistics of things, unlike convolutional networks, which are designed to learn like the spatial statistics. Anybody seen this? Sunspring? No. You know who that is?
That's Thomas. He's in Silicon Valley.
Exactly. Yeah. Thomas, what's the middle ditch?
Middle
ditch. Yeah. Also, I can't remember. So a couple of, I think it was last year, maybe a year and a half ago, another network was trained to on like I don't know how many, like tons and tons of sci-fi screenplays. And then it generated in the same way that this Harry Potter thing generated. It generated a whole script for a movie, and so the script is fun to read. But then they actually got some like real actors and made it, and it's this like 9-minute awesome video. So you can this is what it generated. So this is cool again too because again it was generated on these scripts. And it learned to produce things that look like scripts, right? So like it has not only like the text, but it puts it into context, like who's saying what. It has I'm not sure how to call that, but like it's giving you the setting of where you're at. So like that, I think that says that's something like interior of the ship, and it's got the actions in between. I mean, so they actually go and do this, and maybe if there's some time, we'll take a look at it. But it's super cool. It's again, it's like it definitely feels sci-fi, but at the same time, it's like totally not right. And this is something known in like AI as the uncanny divide. It's known as the uncanny divide, and this is like as good as these things get. Most of the time, there's just this divide that you can't, like these systems never cross. And like we clearly can see that they haven't crossed them, But things keep progressing, and maybe one day we won't know the difference, and then we'll all be in trouble, because then we'll be taken over by these things. Okay, here's some more like generating of things. So this is an image generated by a network that was trained on pictures of like in the insides of houses. So this is work that was done prior to the original, like the faces stuff I was showing at the beginning. And so it's not quite as sophisticated. It's not quite as high resolution. And if you look at this, like again, it's like learning to generate what looks like the insides of houses. But if you take a look at that for a while, you'll realize that like lots is wrong there, right? Like there's something really wrong with the floor, and the rug, and how it kind of like the rug and the table kind of come together. Like there really is no ending to like the one side of the couch over there where the other couch begins. I mean, it's not that bad, but it's not quite right. So it's like learned a lot, but not quite enough. Same thing here, like trained on, like I actually don't even know. I can't remember what this was trained on. But obviously, like architectural images, like that looks like you're traveling through Europe or something like that. But it's also not quite right. Like like this part of the roof is definitely not how it would have been built.
How big is these training sets?
Just each one is just different. So there's often tens of thousands to hundreds of thousands of images, labeled images. Usually labeled like the faces one, the slide faces one is labeled with like things like like this person has a pointy nose, this person has a mustache, this person has sunglasses on, this person's got blonde hair, this person's got black hair. It's always labeled. So like you can learn the model you learn can learn to like parameterize those things. And so like if you want to like put sunglasses on a person, you can kind of like change where you are in the space and have the same basic image, but put sunglasses on. So it's pretty cool. Like this bus, again, like same thing. It's like almost bus-like, and then same thing here. Like it's almost horse-like. It's very close to being horse-like. This horse just has. I don't even know if that's a second head. It looks like another head, but yeah, head. But it's these things are learning some statistics about the images. But to get the high resolution images for the faces, you gotta work a lot harder. There's a lot going on right now with all. There's so much going on in self-driving cars. There's lots going on. This is interesting for two reasons. This is showing networks that can take a frame like this, and they can basically like separate out all the objects that are in this image. So like it knows that this is a car here, distinct from that car here, distinct from that car there, distinct from that bus there, distinct from the road, distinct from the front of my car, distinct from the trees in the back. This is a really good image right here. Like these are all distinct cars. Like it can really quickly make that call, which is important for doing self-driving cars because you don't want to run into other cars. Although this is not necessarily how this is done. Usually the main signal comes from something totally foreign, not video, but from like something here like LiDAR, which is a different technique, kind of a scatter technique to be able to detect depths of things. And this, the sampling of this is much higher. So like there's lots of sensors being used here. So we're gonna mostly focus on things like images because we do a lot of computational networks and stuff. But people are doing very sophisticated things applied to all kinds of data sets, not just text and like RGB images. You probably know about this by now. There are techniques called reinforcement learning that can, that are part of like the deep learning, or just the machine learning, just the types of learning you can do. Reinforcement learning uses signals about like, in this case, did you win the game or not, to learn to like play games. And a couple of years before this, DeepMind had trained networks to play chess at like super high grandmaster levels, but it was always thought that Go was going to be this game that nobody could crack. And then this is now how long ago? Like a year and a half ago, kind of forgotten. And I think that's Lisa Dahl in this picture. So one of the like the greatest Go players of all time, and was soundly defeated by AlphaGo. And AlphaGo had a lot of heuristics about how to play the game built into it. DeepMind followed this up with something called AlphaZero, like a whole a whole new idea for how to do these things called AlphaZero, and they have an AlphaZero Go, and which doesn't have necessarily these heuristics built into it like was done here. And you basically learn to play this game just by playing itself over and over and over again, and it plays at the highest levels as well. So I mean, impressive because Go is a really complicated game, and there's tons and tons of moves from beginning to until the game ends. But nevertheless, learning just from data how to play in these games. Games work right now because games have very rigorous state definitions, and you can often be described in very simple finite state machines, or can be broken into kind of approximate things like that, and it makes it easier to do tree searching, Markov tree searching. But nevertheless, these things that were thought that would be really hard to do are already done and beaten. Now people are moving on to the next things. Yeah. So here's the thing I was saying earlier that was kind of scary. There is volume here, or there's sound here, and I want to, let's see. I want you to be able to hear this. One second. Okay, let me get the volume up on this. Stupid Mac keyboards. Okay, I might need to do this. I'm not sure how. So we'll go. Okay, anybody seen this already? Mm-hmm. Yeah, it's these things are kind of getting famous now.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. It's a time when we need to rely on trusted news sources. It may sound basic, but how do we move forward? In the age of information is going to be the difference between whether we survive or whether we become some kind of fucked up.
Whoops, sorry. He was coming down. And then he says, "Stay woke, friends." Pretty, and these are getting better now too. How is this done? This is actually another generative network that has learned to associate the audio signal with how to move the mouth, and then just put it in the right place on his face. This is getting, if this doesn't worry you, you're not thinking deeply enough about it, because this is really a big deal. We consume so much of our information, through short, sound bites and things like that. How do we know what's real and what's not real? It used to be pretty easy. Now I think it's a lot harder.
I was thinking, do we have to start signing our YouTube videos with PGB keys or something?
Yeah, I mean, I don't know what the answer is, but these are getting more and more sophisticated, and it's all neural networks. There's no other technology beyond the neural networks. So you're going to learn something here that's going to be a foundation for being able to do some really great good in this world, like maybe try and cure some diseases, or you can go and impersonate, famous, powerful people, and the choice is definitely yours. I would hope that you take kind of the morality of what we're doing kind of seriously, and we're not going to spend time kind of talking about it as the ethical issues here in this class. We just don't have time for it. The very last lecture of this class, we will take some time to like talking about the limits of deep learning. But anyways, just wanted you to, you hadn't seen that before, just know kind of how scary this can be. And you're going to learn the techniques for doing it.
So you said that you use it for these images that you use like to find treatments or something. In all these pictures, we were able to identify what was wrong. How, when you're presented with new data, how do you evaluate how good it, or like
If it's real or not, are you talking about like?
Not like, I mean, things that are actually, I mean, that matters, but like something life-saving if you're plugging in data into these networks.
Yeah.
And clearly
So,
they haven't passed.
Yes, that's a really interesting question. So because we need to kind of keep going on, I'm just going to give a kind of a terse answer, but maybe we'll talk about this later. But there is no real like artificial intelligence yet, right? All that these networks learn to do is learn the statistics of the data that they're trained on. That is it. They are awesome at that. So we've always had that. Statisticians for a long time have shown us how to learn like how to fit a Gaussian. This is what this is doing at an extremely sophisticated level with extremely like complicated probability distributions. That's all that's going on here. There's nothing else. There is nothing else. Artificial intelligence will come when like that is when like there's some, in my opinion, some ability to reflect on what's happening and like the whole process of like input and output and like the consequences of that. But I said you have to work, so I've been shut down already. This is the last lecture. Sorry. I don't know what happened there. It's not my machine.
You were low on battery,
Yeah, I'm a little low, but it's my laptop's still going here. It's just right there. I'm not going to do this. It's these lamps of lights turned on. Turn it off, turn it back on, see what happens. Here we go. The classic Windows solution. Okay. So just briefly, just tell you a little bit about this course, what to expect. This has been published. Hopefully, you can see it. Last time I taught this, I had a learner use Canvas, and now I'm like expert Canvas user. So I already have it ready by the first day. But you can go there and kind of see the syllabus. Just kind of give you just a basic overview of this. We do have 3 TMs for this class. There's a difference between TMs and TAs, I've learned. Alessandro Ferrero, he was the TM in our course last time around. He's also in the TM again this time around, which is great. He was fantastic. He helped a bunch. But he's still finishing up an internship and won't be here until next week. We also have Surajit as one of the other TMs, and Prince is the third. And you can look here and see where their office hours are, and get to know them because they can help. They can help when you need help. There really is no textbook for this course. I'm gonna provide the slides that from these lectures, and there's references to other places to go. If there's any textbook for deep learning right now, it is this one right here by Goodfellow and Bengio and Corville. So that's an online text as well, so you don't even have to buy it if you can stand just looking through the HTML. And there's a couple other things here as well. And like this course right here, which has been taught at Stanford for a number of years, is a place where I've taken a lot of material with permission from, because it's just such a great course in teaching deep learning, especially on the convolutional network side. There's going to be 4 homeworks. There's going to be 4 homeworks. They're all going to be distributed as Collaboratory notebooks. When I taught this last time, I was like, there is not a single GPU resource on this campus for any of the students. So I was like, how are we going to possibly do this? But Google Cloud came to the rescue. I don't know if you've ever used this before, but Collaboratory is basically just like Jupyter notebooks. They're hosted on Google Cloud. They give you they have different runtimes available to you. So you can, the default's a CPU runtime, but you can also default to a GPU runtime, and now even to a TPU runtime, which is like a specific ASIC for deep learning GPUs now. But so, anyways, it's really cool and it's free, and I distribute all the homeworks as Collaboratory notebooks. There are going to be these 4 homeworks. There's not going to be any exams, and there's going to be a final project. And you have to do it in groups. If you don't do it in groups, you'll get a 0. It has to be done in groups. You have to learn to work together. Sorry. So find a friend. Find somebody you can at least work with so you don't get a 0. But it's got to be in groups, 2 to 3. So it has to be 2, can't be more than 3. And this was a lot of fun last time. Lots of creative things came out of it. I learned a ton of things about like how networks are used, like they're used for encryption. I didn't know that. And now I do. So anyways, you can read some more about the details there. They're going to be due the last day of finals, so plenty of time to work on it, right? When it comes to computing, I just said we're going to use Collaboratory for pretty much everything. If you need more than that, I did get Google Cloud credits from Google. They're really nice. They've always provided these when we needed them. So I got them in like increments of $50. That's basically, I got like basically 1 for every person who signed up for the course. You can have that at any time. I would suggest not using it right now. You can do all the homeworks and stuff on in Collaboratory in the runtimes provided. But you might want that for your final project because you might need like a little more compute than what you can get in Collaboratory. But most people did their projects in Collaboratory as well. So the projects are not meant to be like, like you're a publishable research project. It's meant to be like something you're interested in that you can apply deep learning to. There is going to be a homework 0 that's worth nothing. But this is important, and I'm speaking on behalf of Alessandro, who was the TM last time. So I should have spent more time with this. Sorry. There are a few prerequisites here. One of them is that you must know Python. So I think Python is particularly easy to use if you already know something else, but you have to know it, and you cannot expect the TMs to teach it to you. The TMs have no responsibility to teach you Python. Do not come to them in a panic saying, I don't know how to do this, and it turns out you don't know how to program Python. If you're coming to this class and you're like, oh my gosh, I've never used Python, that's okay. Like the basics of it you can learn pretty fast, but you better learn it soon. So I hope that's really clear. The homework 0, which is available now, is a way to assess yourself, like, do you know enough Python to kind of get going here? Please, even though it's worth nothing, because I don't want this to affect your final grade. I want you to just go take the assessment for yourself and just kind of evaluate yourself. Make sure that you feel comfortable enough with your abilities to do Python. So you have this week and next to do it. But please do not. So like last semester, Alessandro had to basic in the last minute many times teach people basic Python rather than them teaching it to themselves. So he does not want to do it again, but I don't blame him. We're going to be taking a lot of derivatives. Gradients are a big part of what we're doing. So just got to know some calculus, linear algebra, and everything that we're doing here. Got to know some linear algebra, but you don't have to be masters in this. It's just, can you take partial derivatives and, can you, do you know a little bit about what a matrix is? What its whole job in the mathematical universe is. Some basic probability and statistics. Again, not a ton there. And then, if you have familiarity with machine learning, that's great. We are, the first couple of weeks here are going to be pretty, we're going to review a lot of things in machine learning, not necessarily to review them, but they're part of, understanding what it is we're doing with neural networks. So it would be great, but, it takes a little bit of time. If you've never done it, if this is your first machine learning course, take a little time to figure out what the heck machine learning is besides, something that's going to get you a lucrative job someday. There's a lot of things that I'm not going to stop to do that you should be aware of. So there's a zero of homework that's available now. It's just it's on the assignments here on Canvas, and then we're gonna have 4 other homework assignments. Each worth 20%, and then there'll be a final project, and it's worth 20%. So everything's worth 20%. So just do these things. It's not easy, but it'll be good. You'll know a lot about neural networks when this is all done. And then, like I said, you can go take a look. I won't go into this in depth right now, but you can take a look at this. And you know what? I'm gonna need my power adapter. And I don't think I have it with me. Never think about it. Shoot. Anybody have a USB power adapter? A USB MacBook power adapter with them? USB-C? Anybody ready? Take a look.
Google Pixel. Will it work?
I don't know.
You've got this one.
Oh, perfect. Yep.
Also, what is the actual link for the homework? Because on
I can just oh, okay.
on the assignments page, there are no assignments. So
Yeah, they'll be there when they like here in the syllabus. There will be the homework one will become available in that week. Does that make sense? So there's like 3 weeks to work on that homework one. There's 4 weeks to work on the next one, and so forth. Is that the question you're asking?
as long as homework 0 is not supposed to be an assignment.
Homework 0 is in assignments right now. It should be. If you don't see it, let me know.
I don't see it.
Okay, maybe it's not published yet. It's there. I will put it there. I will publish it right now. And where's my power strip here? Heaven's sake.
Can you build power homeworks ahead of time?
This plug over here. That's a joke. We do need this long. It was a power strip last year. Okay. So did I answer your question?
As long as it'll be there, yeah.
Yeah. Okay. Good. Yeah, I think I didn't hit the publish button on it, so I'm not an expert yet. Let's fix that.
Can you move your laptop onto the shelf or whatever, like the gray one?
I'm going to burn out. Just going to leave. Okay, thanks. Thanks, Suji. Anyway, so this is the plan. We're going to spend a lot of time here, learning about some of the basics here that pertain to neural networks. Like we need to know about loss functions and how to optimize them. We need to know some basics around like some very basic neural networks and how that works. We need to get into the basics of convolutional networks, understanding them, talk about some of the deep learning frameworks that exist for doing this kind of training, and like how to use them. And then we'll get into more like specialized uses of convolutional networks. These generative networks are going to be like some of the things that they're the models, they're the tools that we use to do some of the fun stuff that we just saw. Recurrent networks for like the text-based or like temporal-based things, and then some reinforcement learning, and then we're done. In the last week of lectures, we won't have lectures. This will be just time to work on your projects. You turn them in, and we'll be all good. Yeah.
Will we cover the?
See what? Homework 0. Oh, sorry. No, just for me. I think I did publish. Okay, go ahead.
Will we cover the transformer architecture in this aspect?
Say it one more time.
Will we cover the transformer architecture in this aspect?
We will do that probably in the like on the 4th of the 4 lectures for the recurrent networks. Yeah. I say probably because sometimes things just change from the original plan, and like there's a lot to learn about recurrent networks before getting to like a very more recent sophisticated things. So sometimes we may not get all the way to that, but like that is one of my goals. To talk about that and BERT, which is like one of the most used and useful transformers right now. Okay, I think I just got published. Will you check that?
It's there.
Cool. Thanks for checking that. Question?
Well, you said the time from release to submission is about 3 weeks. Is that how long these homework assignments will usually take?
I mean, it's just different for every person. Some like like the first one will, I think you'll find to be surprisingly long. Because it's basically going to give you like a whole bunch of like template code, and you got to fill in the gaps. And it's you know, if you haven't done, like, if you're not super familiar with like NumPy in Python, or you know, yeah, basically, like, if you're not super comfortable with like manipulating arrays in NumPy, there's going to be a learning curve there to figure out how to do it. But if you are already, then it will probably get a lot easier. But Python, for whatever reason, Python is like the language that we do deep learning in. All the frameworks they're not written in Python, but they have Python APIs. And, you know, data manipulation is all in Python anyway. Python is the thing, so this is a Python class as a result. Other questions?
Sorry, and what are they written in if they're not written in Python?
You know, like a lot of them are written in like C++, C. I mean, they're like NumPy itself is actually just a wrapper around like C arrays and things like that, in the manipulation of them. Python is not good at, it's not fast and good at those kinds of things, but it's an excellent like API like wrapper layer. So so a lot of things are just exposed that way, and there's like lots of neat tools for being even closer to those things like Cyclone if needed. But yeah, they're written in different ways. But you never interact with them at that level unless like you're building out like a TensorFlow, like new operations, in which case you have to go down to these lower level languages. Okay, let's see. Okay, any questions? Any more questions about course details? Okay. I think it's likely that a number of you are probably wondering if you're going to be able to get a permission code to join this class. I know a couple of people have emailed me about that. The class, I think, as it stands, is full in all the sections. Although that at this time of year, it bounces around a bunch. Some of you may need permission codes because you're not in CS or math. We should talk if that's the case. If you are in CS or math, you should be trying to get into the sections. And I won't be going above the number that's there because it's otherwise just too many people. So just so you know, maybe I should have said that earlier, but happy to talk to you if you think you have like a special case. We can talk after class here. Okay, so let's just briefly, in the time that we got left here, let's talk a little bit about machine learning. What exactly is machine learning? So, so there's a book written by a professor named Tom Mitchell, and this was his definition that he wrote in this text. So like, you'll see this all over the place when we talk about machine learning. So, a computer program is set to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. Clear as mud, right? I don't know. There's machine learning is kind of a big topic, and there's lots of boiling it down into like statements like this aren't even that helpful. It might be more helpful just to be like to learn from particular examples. But one way that I like to think of it, not all problems can be posed this way, but I think this is really helpful and want to share this. So I think of machine learning. What are we going to do? What are we trying to learn? So we're trying to learn the structure of the observable world. So I have structure in quotes, I have world in quotes. So what does that all mean? Well, our world might be, again, like faces of celebrities. So the world is really like what our data is sampled from. So it doesn't have to be the whole universe. It can be something very narrow, like straight-on pictures of famous people. That could be our world. And what we're trying to do is we're trying to learn the structure that's in that world. In this case, like in this pile of data. So this might be, this is telling us something about the structure of that world. Some of you laughed. You laughed because like something's not right there, right? So is is this an arrangement of pixels that's in our world or not? Well, okay, so I heard some yeses. Anybody want to say no? Well, it totally depends on what you define your world to be. You are in charge of your world. You get to decide what that is. And if I decide that I want pictures like this in there, great. But if I want to be able to generate faces that look good, that look like real faces, I won't have that in there because this doesn't look like a real face. Because something's wrong. You probably can't even tell what it is, but something's wrong. What I love about this is that you just flip that picture around, upside down. It looks right again. But it's still wrong. It's still wrong. It's just this picture turned upside down. But it's just the way that our eyes process the information. Yeah, I love these kinds of things. So a way to think about the structure in the world is to think about all the possible configurations of pixels. So this world, back up. This world is going to be, images of this size, and maybe they're color images. So maybe there's 3 channels: red, green, and blue. Maybe they're all grayscale. I don't know. But in this world, what we want to do is we want to assign probabilities to certain arrangements of pixels that are likely to exist in this world. That's one way of getting at the structure. It's a very useful way in machine learning. So in this first one, we want to say that the probability, the likelihood of this arrangement of pixels is very high. It's not 0, it's much larger than 0, because this is a picture of a real face. For the second one, we want to say something like its probability should be basically 0. I mean, maybe it's not exactly 0 because maybe it's almost like a real face, but we want it to be really low because this does not look like this is not a real face. And then this other one, you can decide for yourself what your world is like, but because that's just a rigid rotation of that image, it should also be assigned probability 0. So something about capturing how likely an arrangement, in this case of pixels, is in our world tells us about the structure of our world. Okay, so these haunting pictures of Adele are going to continue with this. So a way to phrase this is say something like, let this funny X be the set of all possible configurations of the world. So the structure of the world is described by a probability distribution on that data set. Okay? That is giving us the structure. And when we, a distribution tells you the probability of any one of those configurations. It's telling us how likely it is. So all the configurations of all the pixels are possible within this world of fixed size images in 3 color channels. But some of them are likely or probable, and some of them are not. We are often actually interested in these kinds of questions about our world. What's the probability of observing a particular set of features, we're calling them just generally Y here, given a particular configuration? We might want to know, does this person have long hair or short hair? Or is this person a celebrity or not? Is this person, I don't know, are these eyes narrow or wide? Or I don't know. How do you think about these things? Whatever the features be, it could be anything. We often pose a lot of machine learning problems in this way. We want to be able to learn these kinds of distributions, these conditional distributions, because we want to be able to predict the features Y given the input data, the input configuration X. And it turns out that when we have these 2 notions, we actually have our 2 major divisions of machine learning. Unsupervised learning can be characterized as learning just the distribution of our configurations. And supervised learning can be thought of as learning these conditional distributions, learning the features Y given the configuration given to our model. And our model is simply just an approximation to these distributions. And what I have here is this theta, and this theta is just the weights or the parameters of whatever model. This could be any kind of machine learning model. This could be, this could be a very simple linear regression. This could be a very sophisticated neural network, whatever. What we are fundamentally doing is trying to learn the distributions, the probability distributions of these configurations in our world. And actually, when you think of it this way, many of the algorithms that we use are like very straightforwardly derived from these, from thinking of it in this probabilistic way. And we'll see that as we go through the semester. But yeah. So like, here are these images again. The world here is a particular data set called Celeb A. So we're trying to learn to sample from the distribution that is characterized by the Celeb A data set. So that's like an unsupervised learning problem. We're trying to learn to sample from this distribution. Kind of something similar here. Like again, this describes the statistics of like Harry Potter text, and given some seed, the way this might be thought of as like generate like the next character, the next word, given like a particular configuration of words already. So again, sampling from a distribution defined by the data. So, similar things here. This data set's called Coco. Microsoft curated it. What we're trying to do here is we're trying to, given a configuration of pixels, the image X, we're trying to predict the features Y, which are in this case the words or the caption associated with the image. Yeah, I'm already going through this. There's tons of ways to think about this. This is an object detection algorithm. We'll spend a week learning about these kinds of things. It's learned to like look at the whole arrangement of pixels in these images, and then be able to draw bounding boxes. So like it's drawing Y. This is like a Y from some part of the configuration X, and then not only that, it's labeling what's in there. So it's not only recognizing that there's a thing in there, it's telling you what the thing is. Yeah. Same thing. Hey, here's a set of images around driving. Like in this case, you can think of it like in this temporal way. Given my configuration right now, what I'm seeing in like some history of decisions I made up to this time t. What's the next decision I should make in time t plus 1? Most of the problems in machine learning can be posed this way. Here's a problem in machine learning that's actually difficult to pose. Anybody ever seen this before? This is a moral machine at MIT. Yeah. So if you've never done this before, please go to this and start taking this test. What this test is it presents you all these scenarios, and it's like what should happen in this situation, right? So like it's an empty car, nobody's driving it, it's just a self-driving car, but like apparently, like because of like its speed and these barriers, it can only do one of two things. It can choose to like keep going straight, in which case it will kill all these people, or it can choose to swerve to the left, in which case it will kill all these people. And you get to choose which one it should do. And literally, they're collecting up this information. I mean, actually, they're probably using all kinds of things, but how do you teach a machine to make these kinds of decisions? How do you even know how to make these kinds of decisions?
It's an empty car, isn't it?
It is an empty car.
Right into the wall.
Yeah. So like realize that like the universe here of possibilities is one or the other. Yeah. Going into the wall is a really good idea. But think about it when I don't know. As you go through this course, think about like how do you even know how to do some of the things that we're trying to teach computers how to do? And you'll find that like sometimes it's hard to answer that. This one's crazy, right? It's got people in it. So should it should it crash the people into the barrier, or should it kill the people? And like how do you make this decision, right?
We like set up a point system or something?
Well, the point of this is to like collect all this data, like kind of crowdsource all this data, and to like, use it to train from. It's like, like literally like, this situation might come up or something nearby it, and it will use all this training data that you provided, your moral decision that you made.
Yeah, there's no stop option. Stop.
There's no stop option. Like, I know, like, it feels bad, right? Like the point of this is not to like get out of the situation. The point is like, if you can't avoid the situation, what should you do?
Selfish choice.
Is the walkway like red, so they should have been walking on this one, and they're green on the last one?
That's a good question. I actually didn't notice that. Yeah, like you might make that decision, like, hey, they should have been walking. I mean, these kind of things are so complex, and like, how do you value human life? Like, the reason that they're putting like old people and young people and men and women and I don't know, there's all kinds of different characteristics. It's because they're trying to get you to like make this decision. They're trying to build a data set on which to learn these things. This is crazy, right? We don't have, sorry, 1 second. We do not have artificial intelligence yet. What we have are things that are really good at learning from existing data sets.
How do you avoid bias or inherent biases about race and gender? Because when you try to do machine learning on like criminal databases, it's racist.
Yeah, so like I read, so in the CS department there's Venkat Subramanian, who actually is like dedicating a lot of like his research time to thinking about the ethics of machine learning, in particular about the biases that exist in data sets, because that's exactly right. Like these things learn whatever's in the data. So if the data is biased in a particular way, like in a racist way, it can't help but do that. Now, there are definitely techniques for dealing with it if you're aware of it. And like local companies like HiredView are like really at the forefront of trying to like figure these things out and try to make the decisions they make around hiring to be insensitive to like demographic information and gender and things like that. But it's a real thing that only until like a couple of years ago, but for people like really seriously thinking about like from a research level. So yeah, like that's exactly what this is trying to get you to think about. Is like this isn't just like a magic wand that you wave and all of a sudden like magical AI appears and like all these things are done right. Like this is the most reinforcing, like bias reinforcing thing that probably exists besides like raising your own children. I have 5 children, so I don't know what that's like. Yeah, this just gets worse and worse and worse. So how is any of this possible? These things. So this is a neural network. Somebody's rendering of it. It's a very simple one. This would not be good for like self-driving cars. But this is what we're studying this semester. This is what's making all of the learning of these complicated statistics possible. And it's simply it's simply, let's see what I have here. Yeah, it's simply just a bunch of like numbers connected together by a bunch of weights that like multiply together in linear ways and then get some sort of nonlinear what we call activation applied to them, and they just kind of get passed on hierarchically one layer to another. And somehow this layering of linear transformations plus a non-linear kind of application after the linear layer, and doing that sequentially somehow produces the ability to learn these crazy complicated things. And a couple of weeks we'll talk about the universal approximation theorem, which says that you can actually approximate basically any function, any reasonably behaving function with these neural networks. So like these things are function approximators. They learn. So like whatever your distribution is here, you can provably find a network that can approximate like as well as you want it to. Those networks get very, very good the more you have to approximate them, and so we really can't learn any probability distribution. But the point is that the computation power, especially like in the last 7 years where like GPUs have really been have been used, and more like sophisticated GPUs have been with like larger memory and stuff have been available. You know, the ability to compute these larger, more complicated networks has become available to us, and that's really what's unlocked the ability to do some of these crazy, interesting things. So all I'm showing you here is like, we're going to do this over and over again, but you know, so like you want to learn this relationship between the data and the features Y. You give it the data, it transforms that into this hidden layer H, that gets transformed into another hidden layer L, that gets transformed in some prediction Y hat, and then this thing learns by comparing Y, your prediction, to the actual Y. And we're going to talk about all about like how the difference in your prediction and the actual output is used to update all the weights in this simple network and the more complicated networks, so that it actually is learning to approximate the output. Yeah, let's see. Trying to remember what I'm trying to show here. Oh, yeah. Well, you know what? We will. No. Maybe we'll do this next time. Actually, this particular slide will fit better with what we're doing next time. That's when we talk about it. But that's what we're doing. That is what we're doing this semester. We are learning how to update the weights in these networks so that it learns to predict the output that you give it in the data set. So hopefully that's what you signed up for. And this class usually goes to 6:35, I believe, but we have 10 minutes right now if you want to ask some questions of me personally. Yes. Yep. I'll put all the slides after every lecture up on the campus.